And welcome back. We are discussing 7.2 in this third and final video for the section. We're going to try to tackle, well, we'll say marginal analysis problems. So we'll tackle this guy, and we're going to finish up this learning objective by talking about incremental approximations. We talked about chain rule in the last one. Let's see if we can get where we ought to be. So we had just finished talking about chain rule for functions of two variables, and we're going to, as is typical for us, whether we like it or not, kind of take that one step further. So with chain rule, what we talked about was kind of the standard sort of setup for us, at least it's becoming standard. We're getting used to this in chapter 7. We have some function of two variables, and our default inputs are x and y. And with the chain rule, what we said was if these variables themselves depend on some other variable. Time is an easy one to go off of. If x depends on time and y depends on time, and what we're curious is how does this function overall change with respect to time, then we needed to kind of dig into these x and y variables and say, well, what are their derivatives with respect to time? So this incremental approximation formula is basically kind of borrowing, if you will, that same chain rule formula and saying, look, here's what we're going to do. We'll start with the basic notion that if we were looking for the rate of change in z, which is what we were up to previously, then we would say, okay, we will take a look at the rate of change in z with respect to x. So that's the same. And then the only difference between these two is that now we're saying, let's only consider how much x changes. Not its full rate of change, but just how x changes, which is the same difference on this left side. We were taking just how much z is anticipated to change. And so again, continuing what we were borrowing from chain rule, just as a reminder, we looked at how z changes with respect to y, and then how y changed with respect to time. But again, we're not interested in this rate of change for this problem. We're interested in just how much does y itself change. So this becomes an approximation because as soon as we stop looking at instantaneous rates of change and start asking for small changes in our input variables, then we're only going to be making a prediction about what happens to this function, not an exact value necessarily. Sometimes we get lucky, but usually it's just an approximation. So let's see if we can put this to work. I picked a pretty exciting function to try this out on. It's maybe easier to start with something that doesn't involve products and exponential functions, but we like exciting stuff. So we're going to take a utility function. So utility functions measure typically satisfaction with something. So we'll say business class, consumer satisfaction with a pair of products. And we'll keep it generic. So this is x measures the price of this first product, y measures the price of the second product. They're measured in hundreds of dollars, so we'll have to track that a little bit as we go, but we'll come back to that later. So our actual task is to use marginal analysis. So here is our key phrase that says the thing we're doing is taking calculus and using that to make a prediction. For those of you who were around with chapter 2, we used marginal analysis with functions of one variable as well. We asked, what is the derivative at a point, and how can we use that to make a prediction about what this output of the function would look like for a small change in x. So this same phrasing is being used here. Now our function is of two variables, so we have to figure out how much these two independent variables are changing, but same basic process and same phrasing. So we're trying to figure out how much does this function u change if product A goes down by $1 and product B goes down by $2. We also are given a starting point. A is $30 per item and B is 50. So let's see if we can break out our formula. Perhaps before we do that, just recall we're going to be taking this u function and we're going to have to take some derivatives, first with respect to x and also with respect to y. So if we just take a look at this, I've got x times some stuff with x's in it. And the thing we've been trying to get used to in this section, in 7.2, is the notion that if x gets to change and x is in two different places getting multiplied together, we're going to be having to use product rule. And then the same deal for y. I have a y term times e to the something that has a y in it. So that partial with respect to y is unfortunately also going to need some product rule. So let's see how that plays out. So our approximate change formula, this definition that was just handed to us, looks like the change in u is going to look like the change in u. It sounds like a self-help video now. Partial derivative of u with respect to x times this small change in x. And then we're going to add the y side of this. So the change in u with respect to y, and then how much y changes. You might notice one sneaky little thing about this. We're looking for the change in u, and if you notice, this partial x is basically like a fancy dx. This delta x is also kind of a fancy dx. So if we were able to do algebra on these things, they would sort of cancel and leave us with just a change in u. That's not an accident. That's sort of what this right side looks like as well. And then we're adding on to that. Well, again, if we sort of imagine this is a dy and this is a fancy kind of dy, and if we were able to do algebra, we could cancel those, and that would leave us with a change in u as well. So the units on this kind of map at what we would expect. We end up with something that looks like the change in u when we're done on this right side. But I'm delaying the inevitable. There's some excitement. Okay, so what in the world is going on here? So here is our delta u, our partial u, partial x. Perfect circle there, Mike. All of this stuff is that term. And here is our product rule in all of its glory. And just to track this again, we took the original function, xy times e to the blah. And then we had to do product rule, so that means derivative of x, which is 1, times the other stuff. So the y times e to the junk all got left alone. Plus, now we leave the x alone and we take the derivative of all the rest of it with respect to x. Well, y is a constant. It's being multiplied though, so it's not going anywhere. Remember, if this had been 2 times e to the stuff, the 2 wouldn't have disappeared, so the y is still out there as a product. And then derivative of e to the stuff is e to the stuff again, but times the derivative of the exponent piece. Well, the exponent piece in this case, we've got negative 2x minus 3y, so this is the little bit of chain rule that falls out from that exponent. I mean, it doesn't literally fall out, but that's the piece that comes from chain rule there. And then it looks pretty similar over here on the right side, but we've got partial u, partial y, all of this junk is that derivative. It's, again, product rule because we had y times stuff with e to the y's in it. So again, we've got derivative of y, which is 1, times the x e to the other stuff left alone. And then product rule, we're supposed to add the other combination, so this time we left the y alone, and then derivative of all the other junk looks like x, which is a constant in this case. We're letting only y change. And then we've got e to the stuff. And once more, we've got a little bit of chain rule that kicks out of this because our derivative of this exponent piece, derivative of negative 2x with y as the variable changing, this is a constant. So this is going to be 0. Derivative of negative 3y looks like negative 3. So there's our other instance of chain rule there. Whew. Okay, so that was big, and I guess it's sort of gotten less attention here, but delta x just kind of held on while we did all this other nightmarish stuff with the derivative. Delta y holds on in the end. And I want to do a couple other little simplifications here, but before I do that, I want to say the hard work is done at this point. And I realize this is a lot to do anyway, but if we just use this formula as it's written and plug in all the information that we're given, we'll be fine. We'll have our answer. We've taken all the derivative stuff. But in the interest of tidying things up, just to note that there is a little bit more that we could do with this. And, you know, math teachers, it's hard for us to resist the opportunity to do some more simplification if we can do it. So the thing that we can notice, for instance, in this first set is this y e to the, I don't know when I'm ever going to learn my lesson and stop using yellow, but we have this y stuff and y e to the junk, and all of that is in common. So we're literally pulling this out as a factor of all this stuff. So if we do that, that's the only term, the only factor in this term. So the only thing left is 1. Plus the stuff that's left over here, but let's see, if we take y to the stuff, we'd have an x left over here, we'd have a negative 2, and so we'd have negative 2x that kind of falls out of that piece. Delta X is still just hanging out here waiting for its moment in the spotlight, but it ain't coming yet. And then the rest of this has a similar sort of structure. I'm running out of colors. Cyan, why not? So we've got a term that looks like x e to the blah. We've got another factor that looks like x e to the blah. If we pull this entire thing out, again, just like in the scenario a moment ago, there's only a factor of 1 left. And then in this other piece, we've got a y and a -3, so -3y is the only factor left there. Again, this is a perfectly fine place to stop. So was here 2 minutes ago. But one last piece of simplification we could do, since we love this kind of stuff, is to notice that this e term, this e to the -2x blah and e to the -2x yada yada, is in common to both of these big giant terms. All this stuff plus all this other stuff. They both have this factor in common. So we could pull that e stuff out. And if we do that, the stuff that's left over is a y, a 1 minus 2x, and a delta x from this first. And then we'd have an x factor and not the show, but just the actual factor. And then 1 minus 3y and a delta y left from this guy. So the only advantage to this is it makes plugging stuff in a little bit easier. But if you were in my class and this second line here was your final answer, the thing you use to evaluate and what we're going to do on the next slide, no problem with that at all. This simplification is not required. Okay, so now to actually break out the original pieces of information they gave us. So you might recall they told us that product A, which is corresponds to X, the price, was $30 a piece. And so you're wondering, Mike, why are you writing X equals 0.3? That is because of the sneaky little factor that the units on our product prices were in hundreds of dollars. So $0.300 is the same as $30. Same situation for Y. This is 0.5 because it was $50, if I recall correctly. Delta X is the change in that price for product A. So that change was down $1, so 0.100th of a dollar. And then similar story for Y. Product B went down by $2, that's negative 0.02. And so, put it all together, the change in U is approximately, again, we're using calculus to approximate a change in this value. It's approximately e to the, and then we're just replacing all of our x's with 0.3s, all of our y's with 0.5s. Finally, that delta x thing gets to do something, so we're replacing delta x with negative 0.01. So here's delta x right here. Here's delta y over meow. And so we're replacing those concrete values. You'll notice there are no variables left in this entire expression because we use these 4 initial pieces of information to replace everything that was in that formula. So quick hop, skip, and a jump through calculator or Wolfram Alpha or whatever your technology du jour is, and we get something like that. So if we had to interpret this, we could write, so unit price of $30 for this first product, $50 for the second product, $1 down in price in product A, $2 down in price for product B, and then that's actually going to increase utility by a little bit. Not futility, but utility. So remember, utility is another way of saying our satisfaction with something. So yeah, I guess that tracks. If you decrease the price for 2 products you're interested in, that might have a little bit of an increase in your satisfaction with those things, given that if you can get the same product a little bit cheaper, you might feel more enjoyment from it. So there's one other piece of application for this section, and we're going to try to tackle that in this video as well. So I apologize in advance for its length because we're trying to do a lot in one. So the last piece of application for this section is an economics one, and it's talking about substitute and complementary commodities. So these definitions that I want to give are kind of our official definitions. We say that 2 commodities are substitutes if increasing the demand for one or the other of them results in the other one becoming less popular. So I usually think of this the other way around. If we start wanting one of these products more, if they're substitutes, then that means we're substituting this first product for the other one. So if we start enjoying something more, we're going to enjoy this other product less or purchase it less frequently, because if they're substitutes, we're generally picking one or the other. So So, classic situations for substitute commodities might be, bread and butter or something. It might be coffee and tea, where if people are purchasing coffee more frequently, perhaps the other caffeinated beverage they would want less. Bread and butter work for this complementary commodity. So if one of these becomes less popular, the other one becomes less popular as well. A more realistic, less tongue-in-cheek option might be to talk about fuel prices and car prices. So if you're purchasing more cars, then fuel purchase tend to go up as well, since they're sort of tied in some sense. And if the price of gas goes up, then maybe then gas purchases go down. Maybe car purchases go down too. So they're sort of tied together in that sense. So let's see if we can try an example out with citrus, because why not? So we have some exciting functions here. I've been picking more interesting ones for this section just so we get some complicated problems tackled in the lesson videos. But we have demand for grapefruit following a particular model. We have demand for oranges following the other. So this little sub O thing, the letter O, is supposed to remind us of oranges, and the little subscript of G is trying to remind us of grapefruit. So capital G is the demand for grapefruit, capital O is the demand for oranges. Okay, so we've got P sub G is the dollar price for grapefruit. P sub O is the dollar price for oranges. And the question is, are these substitutes, are they commodity complements, or neither? Okay, so it turns out the definition that we were handed doesn't actually tell us how to compute this. It just says if demand for one goes up, then demand for the other goes up or down, depending on whether it's complementary or substitute commodities. So the way we can actually dig into this and make sense of it is, in fact, to look at these derivatives. I mean, surprise, surprise, it's in a section on partial derivatives, but let's see if we can kind of track this down a little bit. So the basic premise is if the demand for grapefruits went up, so that would be this G thing. If the demand for grapefruit went up, and then we observed what happened to the oranges, either demand going up or demand going down, would tell us this complementary or substitute scenario. So the way we translate that into partial derivatives is we say, well, I know that the price of oranges directly ties into the demand for oranges. If we increase the price of a product, the law of demand says then the demand for that thing goes down. But here's the catch. The thing we're looking at is what happens to the demand for grapefruit as the price of oranges change. So the claim is, all right, if we increase the price of oranges and watch what happens to grapefruit, we can say, oh, look, they're complementary if grapefruit basically act like oranges do. In other words, if you increase the price of oranges and grapefruit get less popular, that means they're sort of tied together. That's this complementary sort of notion. Now, we have to check both sides in order to be absolutely sure. So we'd also check, okay, what happens to the demand for oranges as we change the price of grapefruit? So if grapefruit price goes up, that's what this little subscript derivative thing is trying to get us to look at. If the price of grapefruit increases, what happens to oranges? Well, if it goes down, that is, if this derivative is negative, that means that grapefruit and oranges are being tied together. They're acting like the same product in some sense. So that would mean that they're complementary. The reverse scenario is the substitute one. So you'll notice the only difference between these two lines is that the less than symbols for complementary become greater than symbols. If we increase the price of oranges and people start buying more grapefruit, that must mean that they're sort of swapping out in some sense. That they're as oranges become too expensive to buy, people are going to buy grapefruit instead. And vice versa. So if we increase the price of grapefruit, this says, oh, hey, do oranges become more popular? Does demand for oranges increase if we make grapefruit more expensive? If so, maybe they're substituting for one another. Okay, so the good news about this is basically we just have to take these two demand functions and take their derivatives with respect to the opposite product's price. So this is the thing that, in my experience, students tend to sort of fall down on a little bit, is they'll take the grapefruit demand and they'll take its derivative with respect to grapefruit price. And that's interesting, but it's not informative for this substitute or complementary commodities deal. So we take the derivative of grapefruit with respect to orange price. And let me go back to our function real quick, just so we have a reminder. So here's our grapefruit demand. Derivative of 10, well, we're pretty good at that. That's going to be 0. Derivative of this is super exciting, except that if we're taking the derivative with respect to the orange prices, this whole fraction has no price of oranges in it. This is like a very fancy looking 5 divided by, 4 plus 2. This is just a constant. So its derivative is going to be 0 right now as well. And then the only thing that has a price of oranges in it is this last e to the whatever term. So let's see how this plays out. We're going to have 0 because those constant pieces were 0. Derivative of 3e to the stuff is pretty much still 3e to the stuff, with the only catch that we're supposed to take the derivative of this exponent piece because of chain rule. And the derivative of that exponent piece is just a nice little constant, just 0.04. So chain rule drops that extra factor on us, but other than that, here's our expression. So here's the thing though. What we just figured out was that this is our the rate of change in demand for grapefruit as the price of oranges changes. Well, what we should recall from either our college algebra or our business calc 1 class is that no matter what price you pick, this e to the whatever term is going to be positive. We can't pick any real number for this and end up with this factor being 0 or negative. So there's no way that this demand is ever going to be anything except for positive, the rate of change in demand. So we're starting to get a little bit of a sense that if we look back at the previous slide, if this derivative is positive, then they can't be complementary anymore. The only possibility is that they're substitutes or they are neither complementary nor substitutes. And the way we nail that down is by going to our orange demand and saying, okay, let's try this other combination. If the price of grapefruit goes up, what happens to the demand for oranges? So again, we're mixing and matching. This is the other product's price for this product's demand. Okay, so this is going to erase our notes here, but I'm going to go back to our orange demand function real quick just so we have a reminder what this looks like. So here's our orange demand. Derivative of this with the grapefruit price as the variable. Well, nobody cares. It's going to be 7. Derivative of 7, no matter what our input variable is going to be 0. Minus the derivative of this thing. Well, we got lucky in the last one. The last one, this fraction didn't have our variable of interest. This one does though, so p sub g is going to have to get factored into this, if you will. Minus 2 times the price of the oranges, but hey, this doesn't have a price of grapefruit in it, so this is going to be 0 as well. So really, this fraction here is going to be the main interesting piece. And just because we're going to have to use this, our options are either to take this and do quotient rule, or to be clever like you may have done in a previous calc class and say, well, if we take this and think of it as stuff to the -1, we don't have to do quotient rule. We can just do power rule with chain rule. Okay, so I think that's what we're set up to accomplish here. Here we go. So this is -4. So the derivative of that stuff to the -1 power, the negative would come down, and then our exponent would decrease by 1. And you may be saying, aha, Mike, you have messed things up, which often is true. But not in this case, I think, because this has to have chain rule. And there's your chain rule. Derivative of this price would just be 1, because there's no extra factors there. This is just like our x, basically. And derivative of +6 would be 0. So derivative of that is 1. So actually, if you'd forgotten chain rule here, you would have been just fine. So, don't try to forget chain rule in general, but you would have squeaked by in this case. So here's the thing. We got zeros. We got another 0 from that extra term that didn't have a grapefruit price in it. So really, this is just 4 times that stuff to the -2. And this is another scenario where if you look at this, no matter what value we pick for grapefruit price, what we end up with is an expression raised to the -2 power. You square something, that's going to be positive anyway. So basically, no matter what we do with this whole expression is going to be positive as well. So no matter what price you pick, this rate of change in oranges would be going up. So you make grapefruit more expensive, people buy oranges instead. So both of these things together, these two derivative calculations being positive, means that these must be substitute commodities. Now, if you think about oranges and grapefruit, maybe that was intuitive to begin with. This may back up that intuition, but we can confirm it using some exciting partial derivative stuff. Okay, that's going to be it for us. We'll come back in the next section and talk about optimization.